14 gigabytes of weights will never fit into the 8 gigabytes of memory in a base M2 MacBook Air, unless you use a new engine called TurboFieldFare. Their benchmarks report it generating 5 to 6 tokens per second using about 2 gigabytes. Andrei Mikhailov built it to keep a small part of the model in memory. The rest it reads off the SSD as it needs it. That works because this mixture of experts model only uses 4 billion of its 25 billion parameters per token, which means saying it's too big to fit is the wrong frame, because the model is only too big to hold all at once. So if only a fraction of this model is ever awake, why has nobody been doing this all along? And is 5 to 6 tokens a second actually fast enough to be useful to you? So what actually has to happen inside a fifth of a second? We already know it's doing 5 to 6 tokens per second, which means the actual unit of this problem is just 1 token. Everything this engine does happens inside that tiny fraction of a second on repeat. So once per token, for as long as it's generating, the system has to decide which parts of the model are needed, get hold of them, do the math, and emit the word. And getting hold of the parts is the step that has absolutely no business working fast enough to feel like a conversation and not a hostage negotiation. Which is exactly why TurboFieldFare is so interesting, because one independent developer just hand wrote a custom engine from scratch, rather than extending an existing runtime. It's built entirely in Swift and Metal, and it exists basically to cheat that one impossible step. So the question is, how does it actually pull that off? It comes down to how Gemma 4 is actually built, because it operates like a massive reference library. The official Gemma 4 26B A4B IT architecture is a mixture of experts, which means the bulk of its weights are divided up into 128 distinct experts per layer. So instead of passing data through one monolithic brain, a tiny 8-bit router evaluates the current token and pulls exactly 8 expert volumes off the shelf, along with one shared expert that stays open on the desk. Which means out of those 128 options, roughly 120 experts are sitting completely idle, dropping the active parameter count down to about 4 billion for that one word. And that's the exact loophole this engine exploits, because idle weights don't need to be parked inside your expensive unified memory. They only need to be reachable in time for the chip to do the math. Which means you never really run the entire model at once. You run the 8 specific books you pulled, and the rest of the library stays on the solid-state drive until the router asks for it. Okay, so what is actually sitting in those 2 gigabytes? It comes down to a strict allocation budget, where only the absolute necessities are allowed to live permanently on the desk. If we slow the generation down and look at a single token being born, your resident memory is only holding a 1.35 gigabyte shared model core that's always active, plus the KV cache keeping track of the context. Everything else is treated like a commuter, so the routed expert weights make the trip off the SSD in real time for every single token, pulled out of a custom .gturbo file format built specifically for this engine. Which does mean the whole thing has to be sitting on your disk first. That's about 15 gigabytes of weights you download once. Your alternatives are paying Apple for more memory up front, or renting someone else's GPU by the token, so a one-time download and some disk space is a genuinely cheap way in. That split is where the tiny footprint comes from, and it's exactly how the project's own repository can claim to run Gemma 4 26B A4B inference in approximately 2 gigabytes of RAM on any M-series MacBook. Which is a comically small footprint for a model this size. But dividing the workload this way means the 2 gigabyte figure stops being a magic trick and becomes an accounting budget, where you know exactly what you're paying for. And it means the bottleneck on this machine has stopped being your unified memory and started being the read speed of your drive. So if the bottleneck is the drive, why doesn't fetching fresh weights for every single token just instantly melt your SSD? Because when you pull those 8 volumes off the shelf, you don't immediately throw them back the second you finish reading. Instead, the engine keeps a 16-slot per layer least frequently used cache of expert weights sitting right there on the desk. But a cache of experts would be completely pointless if the routing were random, which means this whole architecture only pays off if the same experts get asked for again shortly after. Luckily, routing turns out to be highly correlated between neighboring tokens, and people testing it in the launch thread were estimating the overlap somewhere around 40%. That overlap is what keeps the read volume survivable, and it's why third-party write-ups have been able to verify that 2 GB claim in practice. So the published speed isn't a hard spec, it's an ongoing bet that the next token wants most of what the last one wanted. It pays off often enough to work, which isn't the same as always. So what happens when you take that engine and point it at a real workload? Well, you immediately hit the architectural wall, because decoding runs in a strictly sequential, single-file loop with zero batching, meaning you can't share the cost of those SSD reads across parallel requests. Your prefill gets processed in chunks of up to 128 tokens at a time, which is fine, but you run into a much harder ceiling when you look at the memory. Google's own card lists a 256,000 token context window for the Gemma 4 family, but the KV cache is one of the 2 pieces that has to stay resident in your unified memory, so a long, sprawling conversation just slowly eats the exact budget that made this stunt possible in the first place. And then there's the question of what the model actually outputs when you ask it to build something. An independent test ran this exact model through LM Studio against a standard coding suite, and it scored 33.33%. Out of 21 coding cases, it failed all 21. So the engine does its job, but the job most developers would immediately point it at is the exact job it's worst at, which is the model's problem and not the runtime's. But it still means your adorable, friendly local endpoint probably shouldn't be writing your production backend. Okay, so if the code quality is entirely the model's fault, what's left to blame on the engine? Well, we've got to talk about what all those cache misses are actually costing you. Every time the router asks for an expert that isn't sitting in that 16-slot cache, the engine has to go fetch it. And every one of those trips is a literal physical read off your SSD, and physical reads cost power. Which brings us to a cheerfully titled 2026 archive paper called SSD Offloading for LLM Mixture of Experts Weights Considered Harmful in Energy Efficiency. Now, to be fair, they were studying this architecture in general rather than measuring TurboFieldFare specifically. But their argument is that constantly hammering the drive can multiply your per token energy consumption by close to an order of magnitude. So the tokens per second figure you see in the terminal was never the whole price. The rest of the bill just arrives as battery drain and drive wear, measured in a unit nobody ever quotes on a benchmark table. So then, who is this actually for? Because it turns out the 8 GB Air was never really the target market here. The exact same model already ran on 16 GB Macs months before this engine even existed. You could just use plain llama.cpp with the GPU layer set to 0 so your CPU handles the work. And that actually gets you 6 to 10 tokens per second, which is noticeably faster than the miraculous 8 GB unlock we just spent all this time talking about. But if you put this same SSD streaming engine on a 24 GB M5 Pro, the project's own benchmarks report 24 to 35 tokens per second. That's roughly a 5-fold swing on identical software. So the performance scales, but you also have to remember TurboFieldFare isn't a general runtime, because it deliberately runs exactly one model, Gemma 4 26B, and absolutely nothing else. Which means if it only supports a single set of weights that already ran better on machines with a bit more memory, this was never actually a practical laptop product for you to use daily. The 8 GB Air is just a proof. And the thing about proofs is they get chosen for being incredibly hard to pull off rather than for being broadly useful. So what did 100 failed experiments actually prove? Well, what the project actually ships is a local OpenAI-compatible server with streaming and tool calls that reuses a cached prompt prefix, which gives you a real functional endpoint on a machine that previously had no business hosting one. People definitely noticed, because a third-party write-up froze the project at 2,225 stars shortly after launch. It has roughly doubled since, and the fork count is climbing with it, which is the hard-earned payoff for a developer who ran more than 100 experiments that completely failed before he landed on this architecture. And that persistence matters, because the mainstream frameworks still don't do this. Apple's own MLX-LM currently has an open feature request asking for native mixture of experts SSD offload. So while the demo was run on a base laptop nobody would voluntarily pick for AI, the actual thing being demonstrated is that open models are outgrowing memory way faster than memory itself is growing. And one independent developer's 100 failures got there before Apple's own framework did. Anyways, that's all, folks.